do years. So you guys know where we're going. You still looking now? You put your couple pounds of muscle, you'll have them swimming to you.
Okay, so good morning everyone. Just a quick reminder of what we did last time. So we're starting our slope deflection method, okay? So the first thing we introduced in the slope deflection method is the fixed end moment, okay? What is a fixed end moment? It's the moments at the end of a member here, A, B, okay? If point A and point B are totally fixed, there are no rotation, okay? Or slope, and there is no deflection at point A and point B, okay? The fixed end moment magnitude value will depend on what type of loads you have on the member, okay? So we started doing this last time, so in order to find those fixed end moments, we started with a concentrated force right in the middle of the member. So we have P here over a member of length L, right in the middle, and we want to find the fixed end moment. So how to do this? We drew the bending moment diagram. We don't know how much is MA, we don't know how much is MB. They are equal due to symmetry, but we don't know how much is that moment M at the ends, okay? So we used the method of superposition. We drew the bending moment diagram for just P, having P alone, okay? And we had the moments separately on a different beam, okay? So, and then we draw the bending moment diagram. This is the bending moment diagram for just P alone, the concentrated force alone, and this is the bending moment for the moment, and then we sum those up. And then we apply this on the conjugate beam, okay? So this is the load now on the conjugate beam. The conjugate beam is just a free beam, okay? There is no supports for it. This is, you know, how the conjugate beam is going to look like. And then from the equilibrium of this conjugate beam, the summation of the forces are equal to 0. So we equated this force with this force, okay, to find the magnitude of that moment, and we realized that the fixed end moment is PL over 8. And we said you have this at the back of your book, okay, you don't have to memorize it. Although for a fixed moment and a uniformly distributed load, I hope you would memorize them, but anyway, if you don't, I will give you, you know, those values on the test, okay? So for a concentrated force right in the middle, it's PL over 8, okay? Now let's find the fixed end moment for a uniform load. We're going to do the same steps, okay? So, but now for a uniformly distributed load. So the fixed end moments for a uniformly distributed load. So here we're going to follow exactly the same steps as we did with the concentrated force right in the middle. We have a member of length L, that's point A, that's point B, okay? We have fixed end moments here, okay? M, again they are symmetric because the load is symmetric, okay? The load, let's say here we have W, the intensity of this uniform load is W, okay? It can be, if it's in the US custom units, pound per foot, or SI units, it's kilonewtons per meter or newtons per meter, okay? We want to find how much is M. So to do this, again, we're going to split our beam into two parts, or the loads on the beam into two parts. Beam 1, okay, where we have only the uniformly distributed load, plus beam 2, where we have the moments M and M. So this is W. So this beam 1 has to be in equilibrium. Okay. So we have here WL divided by 2. We have here WL divided by 2. For beam 2, it's in equilibrium. That's it. Sum them up. That's what you have here. This reaction that we're going to have here, AY, this is MA equal to M. This is WL divided by 2. This is BY. It's WL divided by 2. So I split those forces with the reaction into two parts. This part of the reaction M comes to this beam. This part of the reaction comes here. And this load comes here. This is in equilibrium. This one is in equilibrium. Okay? And then now I will draw the bending moment diagram for each of those beams. How would the bending moment diagram for beam 1 look like? Bending moment diagram 1 for beam 1. How would it look like? It's a single beam with uniform load. From structure 1, how would that look like?
Curved.
Just a curve. The moment at the critical points, the moment here are zeros, and then you have a curve. How much is the height of that parabola? WL squared divided by 8. Okay? So that's the bending moment diagram 1. What about the bending moment diagram for beam 2? You calculate the moment at the critical points. The start of the beam, it's M, but it's negative. And the point B, it's M, but it's negative, and that's it. You connect them by straight line because there are no loading between point A and point B. So here you have M, that's negative, and this one is positive. So you sum those up to find the bending moment diagram for the entire beam. So the total bending moment diagram, you have the curve here, parabola with WL squared divided by 8, that's positive, and you have the moment here, M, which is negative. Okay? So simply this should have been, this curve should have been subtracted from that line. But I'm just drawing it, as two separate parts. You understand what's this curve? This is how the bending moment diagram should look like. I'm just, subtracting it, drawing them far away from each other. Okay? So now, the next step is putting this onto the conjugate beam. Assuming that this bending moment diagram is a load on the conjugate beam. So this is the conjugate beam. This parabola here, WL squared divided by 8, this is positive, and this is M, which we don't know how much. This is negative, we just put it on the conjugate beam. Conjugate beam would be a free beam like this. Free, because it's fixed. The real beam is fixed. So on the conjugate beam is going to be free-ended beams. Okay? So now this is a load, okay? Applied on this beam. It's not the bending moment anymore. It's the load applied on the beam. So now I would like to find the concentration or the equivalent force to each of those loads. So for this load, for this uniformly distributed load, how much would that be? The area of that rectangle, ML, right? It's right in the middle. This parabola is symmetric as well, so its equivalent force is just right in the middle here, okay? And how much is that force, okay? It's equal to the area of that parabola. How much is the area of that parabola? It's 2/3 the height of the parabola multiplied by the length of the parabola. So 2/3 the height of the parabola, which is WL squared divided by 8, multiplied by the length of the parabola, which is L. So here you have 2 and 8, so this is WL cubed, okay? divided by 12. Now from the equilibrium of the conjugate beam, sigma Fy, the summation of the forces in the y direction, is equal to 0. We only have two forces. We have W L cubed divided by 12 equal to ML. So M, which is the fixed end moment at AB, equal to the fixed end moment of BA equals to WL square divided by 12. That's what we wanted to find. The value, the magnitude of the fixed end moment due to a uniformly distributed load. Again, if you look at the back of your book, okay? See here? Yeah? If you look at the back of your book, okay, you will just find this value given right away. Back of your book here, this is what we derived last time. Last time we derived this value for a concentrated force right in the middle. This is the fixed end moment AB, PL over 8, PL over 8. And today we did this one right now, just right now. The fixed end moment AB and BA, they are WL squared divided by 12, WL squared divided by 12. Okay? Those are for a uniformly distributed load. Any question? As you see, we have many values. Okay? What I'm going to do right now, just the last one, okay, that I'm going to do, I'm going to derive this one. Okay? I'm going to derive this one for you. Okay? So now, concentrated force, but not in the middle. We want to find how much is the fixed end moment, for a concentrated force. That's it, not in the middle. It's not in the middle. It can be anywhere. Okay? So now we have a member A, B. There is a force here, P. Okay? The length of the beam is L. This length is A, from point A to the load, and this length from the load to point B is B. To find the fixed end moments, we have both ends fixed. Okay? So now we're going to have the reactions here. We have AY, and we have BY, and we have here MA and MB. So the quick question, is MA equal to MB? No. It's not symmetric. The last two problems, the last two fixed end moments that we found, it was symmetric beam, so the moments were equal to each other. Now, this is not symmetric, so MA is not equal to MB. There are two values that we need to find. How much is MA and how much is MB? MA here, we're going to call this the fixed end moment of AB, and this one is the fixed end moment of BA. Okay? So, how would we proceed? How would we study this problem? Again, we're just going to follow the same steps that we did in the previous two problems. We want to draw the bending moment diagram for this loading. It's definitely tough, so I'm just going to break it down into some, smaller loads or parts of the loads. So I'm just going to break this beam, okay, using the concept of superposition into P here. This is beam 1 plus MA, this is beam 2, plus MB, this is beam 3, okay? Each of those beams has to be in equilibrium. So now I just took this moment here, I took this moment here, so I'm done with the moments. There are no moments other than those two moments, okay? There are no moments here. There are no moment here, there is no moment here, okay? And then this AY and BY are just going to get split among the three beams, okay? How much is the forces that are required here, okay? Let's study the equilibrium. There is some force here, okay? Let's call this AY1. And here there is a force, BY1. How much are those forces? Just study the equilibrium of this beam, okay? This is point A, point B. So from the equilibrium of beam 1, okay, just take the summation of the moments about point A equal to 0. So we have P multiplied by its distance to point A, which is A, okay, minus BY1 multiplied by its distance to point A, which is L, equal to 0. That means that BY1 is equal to PA over L. So this force here is PA over L. Similarly, okay, AY1 is going to be PB over L. Okay? There are two vertical actions here, and there are two vertical actions here, okay? But I'm not going to calculate them. I can calculate them, okay? If I want, this is going to be here, MA over L, and this one is MA over L in the opposite direction. This one is going to be MB over L, and this one is going to be MB over L in the opposite direction, okay? To be in equilibrium, for each of those beams to be in equilibrium. So now, what I want to do is draw the bending moment diagram for each one of those three beams, and then sum them up, okay? So how would the bending moment diagram for beam 1 look like? Bending moment diagram for beam 1. This is beam 1. How to draw the bending moment diagram? Find the moment at the critical points. Here, here. How much is the moment at point A and B? 0. And then you need to find the moment here. This is one of the critical points. How to find the moment at this point? Break your beam at this point, okay? And take the moment here. So it's this force, B, P, B divided by L times this distance, which is A. So here, the moment at this point, let's name this point C, okay? So MC is P, B, A divided by L. And this is positive. This is the bending moment diagram for beam 1, okay? Now we want to draw the bending moment diagram for beam 2. How to draw the bending moment diagram for beam 2? So easy. Find the moment at the critical points. What are the critical points here? Point A and point B. How much is the moment at point B? How much is the moment here? 0. How much is the moment here? MA. Negative MA. Okay? It's bending the beam down, so it's negative. So this is the bending moment diagram for beam 2. 0, and here you have MA. What about the bending moment diagram for beam 3? Moment of critical points. How much is the moment here? 0. How much is the moment here? MB. Okay. Let me draw this here. This direction. Let me draw it like this. Okay. So it's negative as well. So this is the bending moment diagram for beam 3. It's negative MB here. So the total bending moment diagram, you just add those 3 together. Okay? So the positive moment here, we had something that looks like this. PBA divided by L, and then for the negative moments, here we're going to have MA plus 0, and here we're going to have MB plus 0. So it's MA on one side and MB on the other side. So this is MA, it's like this, and then on top of it we added MB and 0 here. Okay? Those are the 3 bending moment diagrams, okay, added together. This is the total bending moment diagram.
So the tip for B would go to the 0 or just go to the bottom of A?
Is it more than MA or less than MB? Right? That's your question? The magnitude of MB compared to the magnitude of
I'm
MA.
saying, like the tip, like the very far edge of MA comes to the 0, but the B comes to the bottom of A.
So MA here, in this bending moment, it's not shown here. MA is connected to 0, right? MA is connected to 0. And then here you have MB, and it's connected to 0. So you're adding this on top of this value. So you just, it's this part. Okay? Is it clear now? So now I have those 3 parts. This is the bending moment diagram. All I have to do, okay, is put this on the conjugate beam. So this is the conjugate beam in red. How would the conjugate beam look like? It's fixed. So the real beam is fixed. So the conjugate beam is free, right? Free beam. Now, let's find assume this bending moment diagram is now load on the conjugate beam. I need to concentrate it into some forces, concentrated forces. So now I'm going to divide it into 4 parts. This triangle here, and let's say this triangle here. Okay, and then the 2 triangles, the 2 negative triangles. Okay, so how much is this force? How much is this force? 2/3. No, not 2/3. 2/3 is the location of the point. 2/3 the length. But this is a triangular load. So how much is the equivalent force to a triangular load? 1/2 the base times the height. So 1/2 the base. How much is the base? A. How much is the height? PBA divided by L. And how about this green force? It's triangular load as well, so it's 1/2 the base, which is B, multiplied by the height, which is PBA over L. Okay? let's draw this one here. How much is this one? It's triangular load. So again, this is 1/2 the base. How much is the base? How much is the length of that triangle? L. So it's 1/2 MA times L. And then let's say we have this one, let's draw it in orange. Okay, so how much is this? 1/2 the base, which is L, times MB. Right? 1/2 the base times the height. Okay? Any question here? So we have those 4 forces. So now, for the equilibrium of the conjugate beam, okay, we need, our target is to find, okay, MA and MB. That's our target, okay? So we have 2 unknowns here, MA and MB. We want to find each one of them. So to do this, okay, I'm just going to label this point here, point D, okay? And then I'm going to take moment about point D, okay, to find how much is MB. Yes?
Seems like the length on that yellow triangle would be longer than the way it looks. So why is it?
You mean this is longer than L?
Yes, sir.
Right.
That's how it looks.
Okay, so I don't know if you took this in school or not, but when you have a right angle triangle like this, okay, so it's 1/2 if this is the height and this is the base, okay, so it's 1/2 BH, right? If you have a triangle with doesn't have a right angle, okay, so you draw this, you know, perpendicular line on the base, right? You don't use this length, right? This is the base, and now this is the height. It has to be perpendicular to it, right? So I'm not using this length. I'm drawing a perpendicular line, which is L, and then multiplying it by the base, which is M. Okay. So now, okay, we have, I'm labeling this point B. So now I'm going to study the equilibrium of the conjugate beam. I'm just going to take the summation of the moments about point D, okay? So from the equilibrium of the conjugate beam, just taking the summation of the moments about point D equal to 0. Okay? So now I have 4 forces, right? 1, 2, 3, 4. Just taking the moment of each of those forces about point D. How much is the moment of this force about point D? 0. It's passing through point D. So I just got rid of MA. Okay? How much is the moment of this force on point D? The magnitude of the force times its distance to point D, right? So now, how much is that distance from here to here? How much is that distance? So the thing is, first, how much is this distance? Sorry, how much is, okay, I want this distance minus this distance, right? Okay, this is this distance minus this distance. So how much is this distance?
1/3.
1/3 L. And how much is this distance? 2/3 A. So it's actually, this is the force here, so this is the green force, 1/2 A, B, so let me write it like this, P, B, A squared divided by L, multiplied by the distance, which is 2/3 A, okay, minus L divided by 3. That's the moment of the first force, okay? So let me erase this. And then the second force, the moment of this force. So it's this force, okay? So we have plus, this force is P B squared A divided by 2L multiplied by its distance. How much is the distance from this point to this point? Okay? So it's this distance, okay, minus this distance. From B to B minus this distance. Right? How much is this distance? 2/3 A. Okay? So 2/3 L, sorry. 2/3 L. From here to here is 2/3 L minus this distance, which is how much? 2/3 B. Okay? So minus 2/3 B. And then I have the moment of this force. If those were rotating in a counterclockwise manner, so they were positive, this one is rotating clockwise, so it's negative. Yes?
Why did you pick B as your point again? What makes that significant?
So that, yeah, I can get rid of MA. I don't know how much is MA and I don't know how much is MB, so my target is to find MA and MB. So taking moment about point D, now just focus on MB.
So if you wanted to, you could put it on MB as well.
Yeah, I can, yeah. So if taking moment about point D, we will find the moment that MB, and then taking moment about this point, you're going to find the moment MB. Okay? And now we have MB, okay? So we have negative MB L divided by 2 multiplied by its distance. How much is this distance? From here to here. No, it has nothing to do with A. 1/3 L. This is 1/3 L, this is 1/3 L, so this is 1/3 L. So multiplied by L divided by 3, everything here is equal to 0. Okay? So let's do some manipulations here. So let's move MB L squared divided by 6 to one side of the equation, okay? And then here we're going to have just multiply this by this term and then this by this term here. So we're going to have P B A cubed divided by 3L. That's the first multiplication. The 2 cancels with the 2, A becomes cubed divided by L. Okay? And then minus the L cancels with the L, and here we have 6. So it's P B A squared divided by 6. Okay? And then here, okay, having this term here, the L cancels with the L, the 2 cancels with the 2, so we have this point here. Plus P B squared A divided by 6. And then minus the 2 cancels with the 2, and the B becomes cubed. Okay? So here, yeah, where is that? P B cubed A divided by 3L. Okay? And I guess that's it, right? I guess we have something wrong here. Let me check. P squared. Okay, this is correct here. B. Okay, so guess no, everything is correct here. So just doing some manipulations. Okay. This a cubed. Okay. I'll just make it a squared multiplied by a. And how much is a? A is L minus b. Okay. So it's p b a squared, and then the other a, it's L minus b divided by 3L. Okay. Minus the other three terms here. Okay. P b a squared divided by 6 plus p b squared a divided by 6 minus p b cubed a divided by 3L. So now we have p b a squared divided by 3 minus p b squared a squared divided by 3L minus p b a squared divided by 6 plus p b squared a divided by 6 minus p b cubed. I don't know. Let's, I guess here we have still something missing. We don't want to have this cubed. We don't want to have any cube, so we're going to have this as b squared and then multiplied by L minus a. So we have, this is the first term, second, third, fourth, and then b squared divided by 3. Okay. Here we have a, and then plus p b squared a squared divided by 3L. Yes. So now, having those terms, this one is going to cancel with this one. Okay? And then here we have this b squared b over a squared. And here we have 3 and 6. Okay? Right? b a squared 3, that's fine. b a squared 6. Here I don't know why there is a, this is 3. Those two terms should cancel with each other. I guess we had something wrong here. Those two terms should cancel. So this one comes here. Let's go through it again, make sure we had everything correct in the calculations. We had this term, 1/2 b a squared divided by L, 2/3 a minus L over 3 plus p b squared a divided by 2L multiplied by 2/3 L minus 2/3 b, okay, minus mbl squared divided by 6. So mbl squared divided by 6. Here we have p a cubed multiplied by b divided by 3L minus p a squared b divided by 6 plus p those two terms here that came from here, this one, p b squared a divided by, yes, this is not 6. This term here, is the multiplication of this term multiplied by this term. So this 2 cancels with this 2, so this is 3 here. So that's the mistake that we had here. So actually this is 3. Okay? So this term cancels with this term here. Okay? So now we have MB L squared divided by 6 equals to just those two terms. As you see, they look the same. PBA squared. Just here divided by 3 and here's divided by 6. So we have PBA squared, okay? Multiplied by 1/3 minus 1/6. Multiply here by 2, 2 here. So this becomes 1/6. So PBA squared divided by 6. So therefore, MB is equal to what? The 6 cancel with the 6. So we have PBA squared divided by L squared. That's the fixed end moment BA. So how does it look like? It's the load multiplied by B, okay, which is the length that is close to B, multiplied by A squared, the far distance squared, divided by L squared. Okay? Similarly, doing the same thing, okay, you can find MA. So similarly, MA, which is the fixed end moment, AB is going to be P, but now it's the opposite. Instead of B, A squared, it's going to be A, B squared, divided by L squared. Those are the fixed end moments, okay? So if you have a beam here with a load P, and this distance is A, and this distance here is B, the fixed end moments, and we were assuming that they were negative like this, okay? And we got that positive sign, so our assumption was correct. So this fixed end moment AB is P A B squared over L squared, and this one is P A squared B over L squared. That's what you have at the end of your book, right? Let me show it to everyone. So that's what you have here. PA and B, so this is P B squared A over L squared, and this one, it's the same formula, but just the A is squared and B is just to the power 1 divided by L squared, okay? So this is the fixed end moment. So we actually derived this one, and this one, okay? 3 of them, okay? We're not going to derive the rest of them. Maybe today, if we have some time at the end, we can have a quiz for you, okay, to derive the formula for this one. Okay? If we have time, I can give you this as a quiz, okay? So now, you understand what is meant by the fixed end moments, right? It's the moments if the member is fixed from both sides, okay? What if it's partially fixed, okay? It's not a fixed end moment anymore. The definition of a fixed end moment, it has to be fixed, okay? There is no rotation, there is no deflection. If it's partially fixed, there is some deflection, there is some rotation, okay? It's not a fixed end moment. how much is the moments at the end if there is some deflection or some rotation, okay? That's what we want to derive now, okay? So, moments due to the unit rotation at the supports of a partially fixed beam. So now we have this fixed beam, point A, point B. There are no loads now, okay? I don't have any loads. But those ends, okay, they are not totally fixed, they are partially fixed. So now let's say that is a unit rotation here, a clockwise rotation at point A, theta A, that is equal to 1 radian. Okay? That's the only thing, the information that I have here. Okay? The beam wants to move, or the supports want to move the beam back to its equilibrium position. So it's going to apply some moments. There will be some moments, MA and MB, that tends, okay, to move the beam back to its original position. Okay? So theta A here, okay, is just 1, the unit rotation. Okay? So here, what I did is I applied this unit rotation in a clockwise direction. Okay? I assume that MA and MB are in a clockwise direction as well as theta A. Okay? So what I did here is I applied a unit rotation in a clockwise direction at point A. Okay? We assumed, or there will be MA and MB, okay? The moment MA and MB will be generated to return the beam back to its original position. We're going to assume that MA and MB are in a clockwise direction as well. Assume that MA and MB are in clockwise direction as well. What do I mean by as well? As theta A, okay? They have the same direction as theta A. Theta A is clockwise. I'm assuming they are clockwise exactly as theta A. Okay? What do we want to find here? We want to find MA and MB. Those are not called fixed end moments. The beam is not fixed anymore. There is a rotation at point A. Okay? So we want to find, okay, our problem here, okay, we're required to find MA and MB. Okay? How can we do this? How can we find MA and MB? Exactly the same way we found the fixed end moments. Draw the bending moment diagram, okay? And put it on the conjugate beam, and then use the equilibrium of the conjugate beam to find MA and MB. Okay? So now, this is what we want to do. So how we're going to do this, okay? You draw the bending moment diagram and use the conjugate beam to find MA and MB. Okay? So now, I want to draw the bending moment diagram for this beam. How would you draw the bending moment diagram for this beam? Find the moment at the critical points, right? And then connect them by straight line. Why? Because there is no loads, right? To draw the bending, to find the critical points. What are the critical points here? A and B. How much is MA? You said 0? No. MA. How much is the moment here? MB. Okay? So that's it. So let's draw those. So it's so simple drawing the bending moment diagram. So at point A, we have MA. Is it positive or negative? Positive. So here we have MA. It's positive. And MB on the other side, it's negative, right? So here we have MB. It's negative. Instead of connecting the 2 points together, okay? And so if you're drawing the bending moment diagram, you should just connect the 2 points together like this, right? So instead of doing this, I'm just going to say, okay, this is equivalent to this triangle minus this triangle. You agree with this? It's the same, okay? But now it's easier. It's going to be easier to deal with, okay? So I'm not going to use this. They are equivalent to each other. So this is equivalent to just connecting this point to this point. Because here you have MA minus 0. And here you have MA minus 0. So adding them together, it's the same. Okay? So now this is the bending moment diagram. I just now, okay, need to put this on the conjugate beam, right? So now, that's the conjugate beam. Okay? This part is positive, this part is negative. So now, I'm going to do an easy step. Just find the equivalent force to this triangular load and the equivalent force of this triangular force. Okay? So how much is this force? It's going up. It's triangular, so it's 1/2 MA times L. This one going down, it's 1/2 the base times the height. So 1/2 MB times L. Those are the two forces, right? And now this is the conjugate beam. Do you agree that this is the conjugate beam? No, not too much. Why? Because here, this is totally fixed. There is no rotation, there is no deflection. So if it's totally fixed, so in the real beam, so it's phi on the conjugate beam. Okay? Here, this is not totally fixed. Right? It's not totally fixed. Why it's not totally fixed? As you see, there is a rotation, right? A totally fixed beam, the rotation is 0, right? Here you have a rotation. How much is the rotation at point A? How much is the rotation at point A? Which is 1. Okay? So there is a rotation at point A. So if I just draw a free end like this, free end, that means that the moment and the shear is 0 at the free end, right? The moment and the shear are 0. So the moment and the shear on the conjugate beam, what do they represent? The moment on the conjugate beam represents the deflection, and the shear represents the rotation, the slope, right? How much is the deflection at that point? It's 0. So there is no moment on the conjugate beam. But how much is the rotation at point A? 1. Okay? So the shear at this point, at point A, cannot be 0. It has to be 1. So to take this into consideration, I have to put some shear force here, some vertical force that is equal to 1. Okay? So that I enforce the rotation at point A to be 1. When I just ask you, how much is the shear here? You take the section here, so the shear is 1. The shear is the rotation, so yeah, the rotation is 1, so now this is correct. This is the correct conjugate beam that represent the boundary conditions that I have in my problem. Any question here? Okay. So here, we needed to put a unit force. At point A on the conjugate beam to enforce the unit rotation at point A. Okay? Now I'm just going to study the equilibrium of the conjugate beam. Okay? So now, how many unknowns do I have on this conjugate beam? 2. I don't know how much is MA. I don't know how much is MB. Okay? So I need 2 equations to find MA and MB. So I'm just going to study the equilibrium, studying the equilibrium of the conjugate beam. The first equation that I'm going to apply, the summation of the forces in the y direction is equal to 0. What are the forces in the y direction?
1.
I have 1. I have this force minus this force. So 1 plus 1/2 MA L minus 1/2 MB L equal to 0. We're just gonna move this to the opposite side of the, of the equation here. Okay, I'm just gonna move the 1. Okay, so here we have MA L divided by 2 minus MB L divided by 2, okay, equals -1. That's equation 1. I need another equation, MA and MB, okay, to solve it with this equation and find how much is MA and MB, okay? So what I'm going to do here, I'm just going to take the moments about point A. The summation of the moments about point A is equal to 0. So here we have 1/2 MA L, this force, times this distance. How much is this distance? 1/3 L. Okay? So here I have 1/2 MA L multiplied by 1/3 L. And then the moment of this force is clockwise about point A, so it's going to be negative 1/2 MBL times this distance. How much is this distance? 2/3 L. So 1/2 MB L times 2/3 L equal to 0. So now I'm just gonna have, and the thing is, we missed something. Do you know what we missed? Anyone remember what we missed? Okay? Anyone remembers what we missed? Very small thing. Okay? Everything we did was correct, but we just missed something, okay? It's important here, okay? We missed it in all the other problems, but it wasn't important. But in this problem, it's important. It's dividing by EI, right? Okay? So here we're just going to have EI and EI here. Just EI. This is equation 2. So now we have two equations having MA and MB, okay? We can just, subtract those two equations from each other after dividing equation 2 by L, okay? So we're going to find that solving equation 1 and equation 2, we're going to find that MB is equal to 2EI divided by L, and we're going to find that MA is 4EI divided by L. Those are the moments at the ends due to the unit rotation, point A and point B. Okay? So, the thing is, just before going, why didn't we divide this one by EI? Because this represents the rotation. The rotation is 1, right? The rotation is, so it's not 1 divided by EI. It's just 1. So now those are the moments due to a unit rotation at point A. And solving the two equations, we will find that MB and MA are positive. What does positive mean? Our assumption was correct. What was our assumption? If the rotation at point A was clockwise, those are going to be clockwise as well. What if the rotation at point A was counterclockwise? They would be counterclockwise as well. So they have the same direction as theta A. If theta A is clockwise, they are clockwise. If their theta B, theta A was counterclockwise, they are counterclockwise as well. Okay? So that's what is meant here by this positive sign. Okay? Now, what if theta A was not 1? What if theta A was 10? How much MB would be? If theta A was 10 radians, not 1 radian, how much MB would be? Hmm? 20, right? How much MA would be? 40. What if theta A was 20? 2 times 20, right? This would be 4 times 20, right? So if theta A was any value other than 1, you just multiply those values by that magnitude of theta A. So for any value of theta A, MA would be 4 EI over L theta A, and MB would be 2 EI over L theta A. Okay? That's very, very important relation that we just derived. Okay? Doing the same thing. So what we did over here is that we had the unit rotation at point B. What if we didn't have a unit rotation at point A? We had a unit rotation at point B, and we want to find MA and MB. It's going to be the same, okay? But just switching them. So similarly, for any rotation of theta b, you're going to have a moment at point B that is equal to 4EI over L theta b, and you're going to have a moment MA at the opposite side that is equal to 2EI over L multiplied by that theta b. Right? Just switch theta A. If you have theta A, MA is 4EI over L multiplied by this theta A, and the opposite side is 2EI over L. If the rotation is at point B, so the moment is at point B is 4EI over L, and the moment at the opposite side is 2EI over L. Right? Just switch the B. That's all. Right? So this is, we're getting closer to what we want to do. We just have 10 minutes. Should we continue or give you the quiz? Continue.
How hard is the quiz?
I told you the quiz, right? Just derive, that formula for the two loads. Let's have the quiz, and let's continue from here next time. So just get a sheet of paper, write your name, okay? And all you need, you have the lectures, right? You can open whatever you wrote today, okay? It's an open book, open notes, okay? There is no problem. All I want you to do is derive that formula at the back of your book. You already know, if you have the book, you know the answer, okay? But I want you to derive it, not just write the answer. If you just write the answer, you get 0 credit, okay? Because you have the answer in the book, okay? So you have a force P here. Force P here. And this is L over 3. This is L over 3. L over 3. And I want you to find, this is point A, B, find the fixed end moments, AB, and the fixed end moment of AB, BA. Okay? So simple. It's easier than the last one that we solved. It's closer to the first two that we solved. Okay? What do I mean by this? It's symmetric. Okay, I'm helping you here. It's symmetric. This beam is symmetric. So simply MA and MB are equal to each other. Right? What you need to do is draw the bending moment diagram. Okay? There will be two parts. Part due to those loads, and part due to MA and MB, which are equal to each other. Just name them M. Okay? Put this on the conjugate beam. Study the equilibrium. Sigma Fy equals 0. You get that moment. It's that simple. And you can check your answer if it's correct or not by seeing the back of the book. Just follow the steps that we did for the concentrated force right in the middle of the beam. Okay? I'm helping you here. I'm trying my best to help you. Just listen to what I'm saying. The previous lecture where we solved for the concentrated force right in the middle of the beam, I uploaded this. You can open your cell phone, just see the lecture. If you didn't write it, it's already posted on Blackboard. There's no problem.